we're going to look at phase changes. In this section, section 3.1, we're going to talk about just general concepts of what a phase change is and look at a phase diagram. And in the next section, 3.2, we'll talk about what causes phase changes and how much energy is lost or gained during a phase change. So here we have a simple plot. Your book has a similar diagram of volume versus temperature for an ideal gas. As you drop the temperature, the volume drops, assuming the gas is kept at constant pressure and you don't lose any gas. Now, theoretically, the gas would drop and drop and drop in volume until really it took up no volume, right? At absolute zero, a gas stops moving. And the little atoms of the gas stop moving and would collapse and form, zero volume. But that doesn't happen. What ends up happening for real gases is as you cool a gas down, you reach a certain temperature where the gas condenses. And the molecules of that gas no longer act as little billiard balls bouncing around, but now weaker forces between the molecules or atoms attract one another, and the gas forms a liquid. Now, when it condenses and forms a liquid, the volume drops quite quickly because a liquid takes up far less volume than a gas does. But it doesn't go to zero. Now that liquid, as you continue to cool it, that liquid will shrink slightly, right? We talked about thermal expansion and contraction with temperature, but still that liquid doesn't go to zero. And if you continue to cool the liquid, for most real gases, then you end up forming a solid. Like carbon dioxide, for instance, forms dry ice. That solid also will shrink slightly as the temperature drops, but a solid, the molecules or atoms are more or less spaced out in a solid, and there's only a limited amount of contraction that can occur as the temperature drops. So the volume never goes to zero for a real gas. Now these phase changes, when does that occur? When does a gas become a liquid? Well, it varies depending on the gas. Different gases have different properties. And we can look at this using ideal gas law, PV equals N cape T. What if we use a closed container? So N remains fixed, right? No gas can leave our closed container. And we keep that, this is a constant, K sub B is just a constant, so that doesn't change. And we keep the gas at constant temperature. So we change the pressure of the volume. We plot pressure versus volume with the right-hand side of this equation being a constant. Right? So if it's an ideal gas in a closed container, so no atoms or molecules can escape, kept at constant temperature, then we get the following equation. PV is constant for a specific temperature. Plotting that on what's called a pressure volume diagram or a PV diagram, we create what are called isotherms. Isotherms are just lines on this graph where the temperature is constant. So here's temperature 1. We can make it up, let's say it's 300 Kelvin. So as the pressure decreases, right, the volume can increase at constant temperature, right? If this is a constant, if P gets smaller, V has to get bigger. Or if V gets smaller, P has to get bigger. So it equals the same constant for a given temperature. So this is the plot, the PV isotherm for temperature 1. Let's say, again, we're just picking a number out of the blue, let's say 300 Kelvin. As we drop the temperature, right, as the temperature goes down, this constant value will get smaller. So P times V is less. So the isotherm drops, but we still have an isotherm here, T2, let's say it's 200 Kelvin. We keep on dropping the temperature down, but eventually we get to a temperature where the object becomes a liquid. So the PV diagram here gets low enough that it reaches what's called the critical point. Now, at this critical point, at a very specific pressure, right, and temperature, the gas becomes a liquid. So at this critical temperature, you draw 2 lines here. To the left of this line, below this point, we have a liquid. So if the pressure is low and the volume is low, the object will become, the gas will become a liquid. In this blue area here, within this blue hump, there is a liquid gas mix, liquid vapor mix, and to the right of this blue hump, it's still a vapor. So whether it's a liquid or a vapor, at low enough temperature depends on pressure. So it depends on the volume that the gas is contained in as well. So we come across this critical point. Critical point is the temperature above which a liquid cannot exist, right? So T3, that critical point, that critical temperature, below that you can start having a liquid. Above that, no matter what the pressure is, no matter what the temperature is, at line T2 or isotherm T2 or isotherm T1, no matter what pressure, what volume you place or what temperature above that critical temperature, the gas will never condense. You'll always have a gas. So at high enough pressure, no matter how much you change the temperature of, say, oxygen, oxygen will remain a gas as long as the temperature remains above a certain value. Doesn't matter how high or low pressure you go. Below this critical point, then you can actually form a liquid. And the critical pressure is the minimum pressure needed for a liquid to exist at the critical temperature. So just because you're at the critical temperature does not necessarily mean you are a liquid or not. It depends on the pressure, right? So high enough pressure, you end up having a liquid. Low enough pressure, it's still a vapor. So that means that at high pressures, you can actually condense gases as long as you're still below that critical temperature. For example, liquid nitrogen. Liquid nitrogen you can form by basically severely compressing the regular atmosphere, the air, which is mostly nitrogen but has oxygen as well, and trace other gases. If you continue to put that under higher and higher pressure and drop the temperature down, eventually the nitrogen will condense out and you get a liquid out of that. So if we want to see at what stages, at what pressures and temperatures an object is a solid, liquid, or gas, we can look at what's called a phase diagram. And we talked about those briefly before, but let's look at them again. Here again we have the phase diagram for water. So we have pressure along the y-axis, and we have temperature along the x-axis. Now there are sort of a y shape here. There's a line going up to the triple point. Remember that this point where they all connect is the triple point of water. That occurs at 273.16 Kelvin and 0.006 atmospheres. That is used to define the Kelvin scale. The triple point of water is always at that temperature, at that pressure. That's the only temperature and pressure where all three phases of water can exist simultaneously. So you have areas up here where in this realm, above this line here, to the left of this line, you have solid, ice. In between this V shape here, we have a liquid, and then below these lines, you have gas or water vapor. So you can transition between a solid, liquid, and a gas, and all of you have done this at some point in your life, right? You've boiled a pot of water. You're effectively you're adding heat to liquid, turning it into water vapor. Keep that pot of boiling water on, and eventually all the water will disappear. You put water in ice cube trays and shoved it in the freezer and created a solid. So to go from a solid to a liquid, we have terms for this. When a solid becomes a liquid, we call that melting. When a liquid becomes a solid, we call that freezing. That doesn't work for just water. Every gas has this phase diagram. Carbon dioxide does, oxygen does, nitrogen does, and so on. We're just looking at it with water vapor. Liquid to gas, going from liquid to a gas, we call that boiling. From a gas to a liquid, it's condensing. And then finally, there's this weird area down here where at low temperature, you go from a solid to a gas or a gas to a solid. Liquid state doesn't exist at this point. Normally when we think of going from a solid to a gas, you have to take an ice cube, melt it, and then boil it, and then you get a vapor out. But you can actually directly transition at low pressure and low temperature, go right from a solid to a gas. That's called sublimation. From a solid to a gas is called sublimation. From a gas to a solid is called deposition. Now, sublimation actually occurs in your freezer to some small extent, right? Ice cubes, if left in a freezer for a very long time, you might notice your ice cubes getting a little bit smaller. If you leave an ice cube tray with ice cubes in for a year, you might notice that the ice cubes get a bit smaller. You get a little bit of sublimation in that process. But it's not the dominant way of transferring solid to gas. So we have here our phase diagram. Then we'll talk about how to move, basically to get from one to another, from solid to liquid to gas and back, you need the deposition of energy.